ongoing. This is basically for the FDM. It's a ongoing, and there are other discussions ongoing in this process as well. So what happens with FDM is like it includes the layer by layer formation, the fiber orientation, including the thickness, how you spray up the resins, each and everything. It's the similar way how you see the automotive composite being manufactured through the molds and everything. With the 3D printing, what we gain is the accuracy. You can get as much accuracy as you want, as much as clear dimensioning, which we cannot get through the standard or the regular molding process, so which the composite parts are of the automotives are being prepared. So this is just a reference I have mentioned in a link. You can go through it. I'm not spending too much time because it's readily available. Definitely, I will be sharing this details with you guys, and you can go through it. Another one important part is uh, second one is a fiber reinforcement in 3D printing. So what happens when you do the reinforcement? This is another part of right now what currently ongoing with the newest technologies and all other areas is like when with the composite there is a criticality of two main thing. One is the glass rovings and the resins. Now when you prepare to the machines, you know that how much you need as an input and what exactly you will get as an output, whether that's a process of pultrusion, hand lamination, or the standard molding. But with 3D printing, what you can do, you can update as on the go as well. You can update whatever the strength you require, whatever the particular portion. If you require more strength, you can update that one as well. That thing is not possible with the standard process. So that's what in a SLA and SLS process we can update. So that's what it is a little bit different with the FDM. And yeah, so that reference is also including, and it's available. If we get more time, surely I would love to discuss that again forward. And now coming to FRP. So what happens with the FRP is like it's a matrix and it's having the fibers. So fibers are of different types. Mostly, we have seen the carbon fibers. Glass fibers are being used when it comes to the pultrusion members or the molding process and everything. Carbon fibers are mostly being used in automotive, aerospace parts and all. Aramid fibers are also used, but they are having a more, what we say, limited applications right now due to the complexity again. It's about the orientation and how you lay up the whole composite material. Then there is a matrix types as well. It's like thermoplastics and thermosets. So love to talk more on this one because that's how the additive manufacturing differs. So on the thermoplastic matrix FRPs, they are actually very easier to process and repair. They are actually very ideal for rapid prototyping. If you want something that needs to be done in a very quickest way, then the thermoplastic, it's your choice to go ahead with that. So all the 3D printing prosthetics using the carbon fiber, they are the kind of best example for thermoplastics in the all the medical applications and everything. This is the thermoplastics are being used because that's required on a very continuous way and very rapidly. Thermosets are mostly used in aerospace and automotive parts because they are the high performance parts. So they require some strength, some impact resistance as well. So thermosets are mostly being used. This is not a limited, it's a typical application. So definitely when you are using and having such certain requirements in a medical field as well, instead of thermoplastic, you can also go ahead with the thermoset as well. So that's this is the just a typical way. So thermosets are also being they are having the excellent dimensional and chemical stabilities. So best example is a epoxy carbon composite in aircraft structures. So whatever you see as a Boeing and aircraft, Airbus aircrafts, The certain parts are definitely made of composites. They are made of carbon fiber composite, and that's the thermoset matrix they are using. Looking at our additive manufacturing process, so melt processabilities, that's an FDM and DIW, direct injection process. That's where thermoplastic matrix FRP are being used. While when there is a requirement of wet photopolymerization, that's with SLAs, when UV curable resins cure into strong and rigid parts, that's where thermoset matrix are being used. Now, I would like to explain a little bit more on that one. So, what happens when, if you see a medical applications of additive manufacturing, that's not gonna directly into the UV affected areas. This is a practical life example I'm talking about. So when it comes, like for example, you have done something for the prosthetic parts or there, or something which is a medical application which is not coming into directly UV part, so you can use a thermoplastic matrix on that, and that's like saving and working as per the feasibility. But if you see parts for aerospace or automotive parts, you see that okay, that's directly going into UV affected areas as well. That requires a chemical stability, and definitely there will be a requirement of impact resistance and everything. So for that you need to have a process of SLAs and everything, and need a thermoset matrix for FRP. So this is why I have focused on this one, and this is why the process differs for the additive manufacturing for the FRP composite. Now, why we are combining both additive manufacturing and FRPs? Like a lot of people think, that, yeah, we can make whatever the last section with the standard of manufacturing of hand lamination and regular process instead of costing with the 3D printing, additive manufacturing. It's definitely costly, but see the accuracy and everything. So AM alone lacks the mechanical strength. So all the additive manufacturing doesn't have that strength. But when you include the FRPs, so FRPs provide you an additional strength because you can lay up the material. You can redirect the material strength in the way you want it. You know that certain in just like for a practical manner. See, whenever there is a joint, we discuss in a engineering, right? That if there is a corner or if there is something which is pending, there will be a stress concentration. Okay, so with FRP, you know that okay, this area, particular region, which is having high stress concentration, you can update that for the particular areas. If you need more strength, you can do it with FRP. So that's why both the combination is working very well, and a lot of development is ongoing. So this also includes the structural and lightweight parts. Now talking about that one, so as I mentioned in a earlier slide that yeah, if it is a UV specific areas, we mentioned that okay, with FRPs and additive manufacturing, we can create certain parts. So that's actually very easiest way, and very quickly you can do it. Now think about something which is going to be on UV affected area or in open area and for the longer period of time. Something which is, for example, on a sea or the near to the beach areas, or going on a mining site or on a telecom tower or somewhere. What you will be feeling like, okay, if I'm going with the standard parts, non-additive manufactured part, it will be like after 4 or 5 years I need to replace it. But with additive manufacturing and with FRP, which is already a lightweight, which is having a part of UV resistance, you can just install that part and forget it about for the minimum 20-25 years. That's how the life of FRP with the additive manufacturing you got to benefit. Also, the lightweight parts are definitely. That's why we are having come up with the additive manufacturing against the standard processes of manufacturing. So whatever you make up with the process of standard, you know that you need to keep the material as a constant. But with additive manufacturing, you can change the material. Like whenever where there is no such requirement, it's just a connection, or you just need to go through it. You can reduce the thickness. You can reduce the material weight for the particular portion. And yeah, you can design it as per your requirement. So that's how lightweight the parts can be made through the AM and FRP. Now coming to the more process, so additive manufacturing techniques for FRP are little bit complex, but I'm just trying to simplify it. Uh, so with FDM, what happens? They use the chopped and the continuous fiber. So what happens is like this is the current process when you see a lot of tanks and vessels which are going to be underground. They are currently made through the filament winding. Yeah, yes, Kavya, go ahead. Hello, Kavya, you have any question? You have raised your hand. Okay. No, this. So, what happens with the continuous, like in tanks and everything? So, when there is a connection, is there? So, they use the chopped fibers and a mat to cover that areas. Now, think about the additive manufactured part with the FRP. What you can do is you can make a small part or actually a part as per the requirement with the thickness and the provision of strength where you need, and you can cover that part. So that's what FDM with the chopped and continuous fibers are working right now. Another one is a direct ink writing. It's the same way like the small additive manufactured machines are currently being used. That's the same process. That's simplest way of FRP designing as well. It's like just going through in the direction of uh, lines and what you need. It's like a simple ink writing stage. That's how you can make. Third one is a resin-based AM with a fiber fillers. So what happens with the resin-based AM is like resins will be already filled, in which the whole materials will be there. You just need to make whenever you need a fibers, you can insert the fibers through the AM process. That's called as a resin-based process. And hybrid manufacturing works in a little bit different way. So it covers the number of process. One is, yeah, you can add FDM, you can add a resin based, and combining both with it's called as a hybrid manufacturing. So hybrid manufacturing is like mostly being used. It's what we say for the smaller part or for custom process and custom products. Hybrid manufacturing is mostly being used, not recommended, but that's right now it's easiest way to have the custom part developed. The next one, coming to our main point, is like innovations currently being done in composite AMs. So, what currently number of companies and number of uh, major product-based organization are doing is a continuous fiber 3D printing. With FRP, you have the fibers, right, which is like lightweight and having whatever shape you need, they are being manufactured. So, in like recent applications where you have seen like applications of automotive parts, you have seen the new lightweight metros and the trains and everything, also the aircraft structure. What you need is a large section. Okay, if you provide a connection in between, yeah, then it increases the cost, it increases the wastage as well. So continuous fiber 3D printing is currently being developed through which you can make a large part. This 3D printing is little bit different than our standard process. Like in a standard, we have certain limitations in the dimension. Here, we are not talking in terms of dimension. It's like whatever you need, whatever the complex size you have, you can use the continuous fiber with that. Think about a tank which is going to be underground. You can make through a continuous filament, continuous fiber, and have that 3D printed, have that manufactured in to the composite. Right now, it's like through the filament winding process, even only on the small number of portion is being used, but there is a development ongoing for that one. Second one, which is quite a good, I like that part very much because it's material functionality graded materials. So what happens in this one is like you don't need a single material. Obviously the composite is itself is a make of two and three parts, so mainly rovings and resins, but also the additives like UV addition, the chemical resistance as well. But what here I mean by multi-material is like, think about something which is having a, composite FRP or the carbon fiber part, then again there is a glass materials only, and then again there is a standard part of aluminum, saying something like, yeah, you will get all the properties composite plus another single material and then again making a composite. That's currently being developed through the AM process. That's nowhere it's possible with the standard manufacturing processes. You can't make it through the heating process. You can't make it through the cold forming, the way you are making the sheet metals and standard metal sections. You can't make this kind of sections in our standard process. But with AM, it's really possible. So that's currently going through the innovations right now. And third one is institution monitoring and quality control. So what happens in terms of like AM processes are quite easy to carry on, and it doesn't require large setups and large areas to have that everything monitoring and controlling. Think about in the remote areas where you need something to be monitored and updation, checking the qualities, or if certain thing is required, you need to manufacture on the that area itself rather than going back to the main plant location and everything. So AM process helps you with that. Small number of parts, small machineries. Definitely, it's a the costing will be another point, but yeah, this is like when you see a remote areas, for that AM is the best thing. And that's what currently being practiced right now, how to reduce that cost and how we can monitor and quality control at the site itself. So these are the innovations. There are a number of other innovations, but I'm just concerning about the top three which are currently ongoing. Next one is the challenges and limitations. So definitely with FRP right now, it's number of challenges are already there with the standard process, and whatever we are doing right now with another, we hardly see number of composite. Like whenever I ask someone, have you seen the composite, and someone says, yeah, on the telecom tower there is a radome which is called white and used as antennas. They are the composite, right? I said, yeah, but that's not only the application. There are a number of applications as well, but the limitations are like we are not using it everywhere. So I'm talking in terms of AM and FRP. So there is a limitations of fiber distribution and alignment. Yeah, we with AM we can get accuracy, but that's from the process, that's from the software itself. If someone has make a slight error, if you have done something wrong with the calculation, you can't change it on the code itself. You need, after the completion of the whole part, or after you get the whole part ready, you will get to know that, oh, the fibers are not distributed very well, or fibers are not aligned as per what the actual product we expect to behave. So that's a major challenge, limitations. Another one is interfacial bonding issues. So we know that glass fibers and the resins, so whether it's carbon fiber, aramid fiber, or standard glass fibers, they need to be bonded with the resins to make a composite material. So with AM, there are chances that it will not bond properly. So it is currently having a challenge. So certain thickness, yeah, machine and software doesn't know the actual practicality. Definitely there is something I will later discuss on the next slide. But yeah, so what happens if you mention something as a 5 of sheet with the made of 5 FRP in a standard additive manufacturing process, then it will be making that shit. But yeah, there are chances that it will not be having a same bond which we are currently having with our politician or the standard molding process, because machine doesn't know that what amount and how it is going to be bonded. So that's an another challenge. Next one is avoids porosity and defects. So in the standard process, we know that okay, for the particular initial time, we will be getting some defects. We need to scrap it. With additive manufacturing, that's the limitations. Like until you start with the process, you will not know that how the actual process. So starting with the small and big one itself, there will be some chances of voids and porosity. So now currently the engineers are working, there is some R&D are going, they have that ideas that okay, this is the amount, like 3% 4% amounts will be there, that these are the chances of having the voids, these are the chances where there will be a porosity. But to avoid that, and that's a challenge, that we cannot have that one when it comes to the number of continuous sources. So that's the part, that's the challenges we are already facing right now. Then yes, there is a limited material compatibility. FRP cannot be, so everyone is aware like composite cannot be welded. So you can't weld or you can't create the something which is going to be welded or something apart from rather than standard bolting process and standard fastening process. So this, that's the limitation. If you have made some part like in a steel or something, you can anyway assemble that complex part, anything with even a standard sections or square hollow section, anything like that. You can weld it across. But with FRP, yeah, you know that it's not gonna be compatible. Even when there is a dissimilar metal, you need to use the, when you having the connection with the standard bolts, and as well you need to have a washer, a nylon part as well, to have that both connection proper, not to get crushing failures and everything. So that's the material compatibility. It's a challenge, and but yeah, definitely with the number of advancement going, this is gonna be resolved in a couple of years or so. This is a now I'm talking about is an application. So our main focus for the whole session is medical, but yeah, still I have mentioned the four major sectors which are being rightly dominant in the whole industry era. So one first one is an aerospace. So in aerospace, you see the brackets, ducts, whatever you see in aircraft. That's the part are being manufactured through the AM process and through the FRP, through the composites. In the automotive areas, the crash resistance part, you see that the front portion of an automobile, if you have seen the car, whether that's a Hyundai, Tata, or even a Suzuki or anything, the bonnet portion, the front portion of the car is made to the composite. Now also with the trains, like what we see as a Vande Bharat, the metro trains, the front part, the nosing part, what we see, that is aesthetically good and that's composite. So whenever have that has an impact, it resists the back portion. There is another the metal parts, and there is also the another persons and other what is the compartment is there, but the front part is all made through the composite and it is made through the AM processes. So in a single design you can make it in a different number of parts. Instead of that, you can make the whole single part in a AM. So that's how the you can manage the cost of AM process and the making it to the different part. Medical, definitely. So all the prosthetics, surgical tools, there are a number of applications as well. Right now, we are just focusing on this too because all the different industries, all there are some rules and regulations as well, due to which it's not being easily applicable for all the medical purposes. But yeah, for the prosthetic and surgical tools, it is widely being used. Not even in India, it's like in American countries, European countries, and even the countries like Australia and New Zealand as well. So I have seen this kind of application. It's largely growing. It's really very good to have this kind of. It's lightweight. You can develop whatever parts you need. Civil, definitely the reinforcement panels are completely made through the AM processes. If you have ever wondered the design of a perfectly architectural part of a architectural building, you see there will be an FRP, there will be a composite part, and there will be a parts which will be definitely made through the AM processes. That's your practical applications you see right away. Whenever you see a building which looks very good, oh, perfectly architecture, yeah, that's a composite and it's an FRP. I have mentioned few reasons here. So this is like currently being used just as a I directly shared the link here because of it's bit of a complex part. So you see that this is the part of a building plate. Now you see the complexity side. Okay, here you see the complexity. How it is being prepared. There are the parts like, okay, you can mention, you can take away the part whatever you need. So that's an use of FRP. There are two different ways. Actually, there is an thermoset and a thermoplastic. Both the composites are there. So this is a detailed example of that one, how it is being used and how they are being currently applied on the civil areas. So it is there. This is the process they are currently using right now. So all that with the robotics and even with the some of them is with the manual cuttings as well, but mostly it's complete additive manufacturing. The main advantage of all this one is like you can make it through the whatever thickness you can, and it's really convenient for that. Now there are two case studies I have specifically mentioned here. So it's first one is a lightweight bracket, what I mentioned in aerospace. So there is an excellent example of one of the companies, Mark Forge. I have seen that example in number of ways, and it's really very what to say useful and hands-on and successful. So this is actually a mounting bracket, which is currently a Mark Forge named company is being manufacturing. So it's going very well. They are having this one completely manufacturing to the AM process with the carbon fibers. This is used in aerospace and defense. This is just one example. You see a number of aircrafts and several military applications as well, where you can manufacture number of different parts to the AM process and with the composites. So yeah, this is one of the best example I have seen in aerospace. Sorry for the duplicate slide. This is a medical customized part. So the one I'm was talking about in medical field. So this is the right now the research paper is already there. So I have gone through this and shared this with number of people. So if you see any project, this is the best example. You see how it is being prepared, how it is being utilized, and why this is the best thing to have a go ahead with that one. You see, a part, a leg is there. You know that this is a complex part. You know there are a number of curvature. Even designing this in a CAD software is a bit difficult. That, but when it comes to AM process, it's pretty good and the best solution to have that developed. Say it is developed in a number of ways with a two process, partition, and a complete modeling as well. Then there is a mentioning of how it is being prepared, how the mold is there, how it is going to be laminated. Obviously, I'm not going into the details, but yeah, feel free to go through it or ask me on that. So one important part is like here, this one. So if you try to make this one in our standard process, you need to have that mold available. Think about making a mold for this one. This will be a very small, plus it's like micron accuracy required for the physical or for the person who will manufacture the mold. And to have that developed, it's gonna be very critical, and there are chances of only 1% you can make it through the manual process. But with FRP, with the additive manufacturing, if you make this one as a perfect in a that model as per the dimension, as per your requirement. Additive manufacturing will be making it same it is. Once it prepared, it looks perfectly fine. It will fit perfectly, and there are the less thickness you can make it. And yeah, this is a live and perfectly successful example of that one. So yeah, that's what two case studies I have gone through, and there are a number of others, but keeping it having the limited time, I'm stopping here. So this is the two case studies. Now, what is happening with the sustainability recycling? Everyone talks about like, yeah, FRP, it's ultimately it's a polymer, it's a plastic. Definitely there are issues. So yeah, there is an issues with the recycling of this material. But with the recycling, there are options as well. You can crush the FRP, you can crush the polymers. There are a number of cement companies and RCC construction industries are there. They require this material as in a crushed way. They are currently using that one in a construction field to have a bonding with the cements. It gives you the strength. It is not gonna break down or it's not gonna melt. So that's why it is useful and recycling that way. Number of other recycling options are also there. Like for example, when you see something to be filled up, when there is a landfilling is required, people are using FRP as well. There are limited number of applications in that. You cannot use more than that, but it's a different way of thinking. Definitely another options will come up when you have this composite part of it. Another thing is the use of bio-based fibers and matrices. So this is another example. You can work on it. That's a will be a sustainable options as well. Another one is a potential for circular economy models. So you know that FRP is made through one process. You can then manufacture or use it in a particular application for the with the AM, and then once you want to change or that product is not further required, you can crush it down, use it somewhere else. So that's how this material can be used for the circular economy models. That's our sustainability and recycling means. Now, talking about the future, what's the future with the AM and with the composite? So right now, it's smart materials and 4D printing option is already there. They are currently being thinking about it. So with the 4D printing, you will be having a more complex part being developed with the AM process and with the composite. Another application is think about AI assisted design optimization. You see, number of we are using AI in a different process, different ways as well in our life. That's the same way AI is also gonna be useful in a just a small period of time in the nearest future that it will be using for the AM process for the composite. Composite is not something that is required for with the number of people and number of what is complexities and everything. So AI can definitely help you with that. AI will be using that as a design optimization. You just mentioned that okay, I need this orientation 60 40 90 or 45 90 45, whatever the thickness you require, whatever the layups you need, whatever the fiber orientation will require, you can just mention three or four options to machines, and the AI will think about it. AI will work on the back end and will give you the best design, optimized design with the AM, and that's how you will get the part. Another important is like integration with the IoT and digital twins. So what here I means by digital twins is like AI is widely being used right now. So connecting that part, that thing with the AM process and that too with FRP will be improving your efficiency. Whatever the parts, different custom parts, complex parts you are being currently being using with IoT and integration of that one, yeah, the more productive information, more productive parts you can make. You can enhance your capabilities and designs, and also optimize it to for the future. So that's current. That's also the future of the AM process with the composites. So yeah, definitely that's my part. You can go through the LinkedIn. I have shared the LinkedIn. Obviously, that's the part of my number. Yeah, you can call me. My number is there, but I would prefer that I'm only having one option. So yeah, you can connect me with LinkedIn on that. If you have any questions, feel free to ask. That's my part. Thank you. Thank you all. Anyone have any questions? So I have skipped through the number of portion. I have limited my content so that because of the time constraint. But yeah, feel free to call me. Still, we have 10, 15 minutes, I guess, left. Right? Any questions, anyone?
Dear participant, if anybody has any question, please to this, sir. Otherwise, we can put a text on the chat
Yep,
box.
yep, sure, sure. I can read it through the text as well. At least you can just give me a feedback like how you see the composite right now. If you have worked on the composite, I would love to hear your thoughts on that one. With AM process, you already have the number of sessions gone. So ask me a questions like how you see AM and composite in your future or in your practical applications. Please go ahead. Yep. Anyone? This is after a long time I'm having a conversation with you guys as a faculty. So I would love to hear that thought. So yeah, I can see three comments. One is Sharanya. Yes, sir. Okay. Devraj Senapati. Yeah, the session is very excellent. Thank you for that one. Follow Satyanarayan. Good lecture. Thank you very much. Anyone else? As a feedback, as a question, anything? Yeah, Madhuka. So hello.
Yes, sir. Thank you, sir. Thank you. So,
Yep.
dear participant, if you want to ask any question, please let us. We have the chat box in WhatsApp also. You can share. Uh, After the FDP, surely we will going to provide the resource material to you. And next, we'll move next to the vote of thanks.
Oh,
Myself,
oh,
Dr. Yes,
sorry. Yeah, Madhuka. So one
yes,
question is
sir.
there from
Yes,
Lakshmi
sir.
Kumari.
Yes, sir.
Yeah. So Lakshmi, you have mentioned like elaborating on how fiber orientation is controlled during the printing process. So what happened is like currently, hello.
Yes, yes.
Yeah. So Lakshmi, what happened is like currently the fiber orientation is being managed through the computer programs. So I would like to say one example which I have recently seen is like there was one automotive parts, small part of a 200 by 170 was required. So in the computer process, the program itself, we gave the orientation that it will be first going to the 45 degree. The 45 degree is how I see as the plotter area. So design as per the 45 degree, then 0 degree, and then negative 45 degree. The thickness was very small, so that's why only one layer was required. But that's how I we started with the 0 point and then the plotter area requirement. So it's like you need to define, you need to see how you are gonna select that start point and how your machine is having that program to as a start point. Have any further questions?
Yes, sir.
Yep.
Yeah. No, no more questions, sir, I guess. And you,
Okay.
yeah, same. Yes, sir. Let's move for the closing comments. Dear participant and our esteemed faculty members and dear participant, I would like to extend my heartfelt vote of thanks to Mr. Hardik Paramara, sir, uh, engineer, structural design and technical at Tradewell Group Private Limited for delivering an insightful seminar on additive manufacturing of composite as a part of our 1 week virtual national level faculty development program. Thank you, sir. Your expertise and experience in additive manufacturing have enriched our understanding of this cutting edge technology. Your presentation has undoubtedly inspired us to explore new possibilities in additive manufacturing. We appreciate your willingness to share your knowledge and time with us, sir. Thank you. Thank you. Your contribution to success of this FDP is invaluable. Thank you, sir. Thank you, Mr. Hatikar, for your valuable presence and impactful presentation from behalf of the organizing committee. Now, I request the participants to fill the feedback form which is shared in the chat box, and rest will be yes, sir. Will tomorrow session. Sir? Madhukar, sir. Dear participant, one announcement is that tomorrow we have the morning hour session. It's 11 a.m. We are going to start the validatory. And yes, sir. Thank you.
Thank you, everyone. Thank you for attending. Yep. Have a nice day.